Presenting our paper titled Using Machine Learning for Intent-Based Provisioning in High-Speed Networks. This is a paper which is a collaboration between Lawrence Berkeley National Lab and HP Systems. Today we are presenting some of our recent work on how we've been able to merge natural language processing with some of our previous intent-based networking research. This idea of intent-based networking actually stems from this problem of tell me what you want rather than how. So the essential idea is that the user should be able to say that what they want from the network, such as wanting the transfer of images to be done as quickly as possible, and then the tools should be able to set up an automated end-to-end pipeline which would enable what the user wants. In today's talk, this is the overview we will follow. We will start with an introduction and motivation, comparing different kinds of intent-based networking projects that exist in industry today, how we were able to actually merge a new concept of machine learning and natural language processing with intent. We will present some of the architecture challenges we had when developing this system called Evian, and then finally we will conclude with results and conclusions. So our intent is focused on user intent. We have the situation where we have a detector which is taking images, and then those data sets need to be generated at 400 megabits per second, transferring into the database. Now this end-to-end system presents a very complex infrastructure problem to the users. They also have to call engineers to set this system up in advance. It's very complex to work around this, and the GUI and the devices themselves are constantly being upgraded. So can we have a system which can automatically pick whatever is available and also update itself whenever there has been a change on the network? With the challenge and the solutions being presented by SDN, which is softwareization of the network, this brings us immense potential that what we can do with networks now once they are being controlled by software. And this is where intent sits. If intent was able to communicate as a software to the network, we could actually do much more intelligence and setting up of the network as needed. So industry has actually been looking into this problem for a few years now, and some of the very famous projects they use is Open Daylight, NIC, and ONOS, where they develop an intent state machine, priorities, they have a conflict resolution, and they also do resource management. Our own solution called Indra was actually targeting some of these problems. They had a high-level language as input, which was not there in the previous sessions. We did do conflict resolution like them. We also did have a GUI intent. However, there were some challenges which we saw in Indra, and then we wanted to re-implement them in Evian to actually remove those and make Evian much more stronger. So before I go into those, let's define what an intent state machine is. This is what is the industry standard right now. So you can start by an installed requirement, whatever the app request says, you compile that requirement and you install it. If it has succeeded, then your network is already set up. If it has not installed properly, it could be recompiling, or there has been some sort of a topology event which is causing it to crash all the time. You could also remove the requirement and then purge the requirement and go down the other route where you can completely stop the system and start all over again. So this is a de facto intent state machine which is now being used in industry, and this is what we actually transferred into our system when we were developing our intent. So our initial implementation called Indra was an intent tool which was presented at C16 as a demo, was the first of its kind because it introduces concept of talking in English to a software system. It did automatic code rendering, and it also used ontologies in RDFs to actually process the intent. There were a few things which were bad about Indra, which we do intend to rectify, was that it was very specific to a certain tools and it was not very extendable. There were no monitoring tools in the system, there was no machine learning, and it was very difficult to deploy. So Evian targets these problems and tries to resolve them as we go forward. So how we came up with Evian's new architecture. So Evian handles some of the issues of Indra. We stripped down the code to new code. We used machine learning for speech here. Now we introduce natural language processing to actually introduce a bot which can talk like a human to the humans. So the bot can now discuss options with users and negotiate. We also separated the bot to have a server-client architecture where the server can actually do optimized configurations. It has multi-tool capability. It's easy to deploy because of the decoupling of these different parts. The bot also communicates back to the engineers before actually automating and rendering everything. So we introduce this concept of a server-client renderer architecture, which is predominantly because of the security challenges of generating this bot. This is the challenge which we see. So we have, using ESNet as an example, which is our network cloud, we can see that we have an edge system here and we have a core system here. The idea is that Evian clients can be deployed at the edge systems where we can do some initial machine learning extraction of entities and negotiations. That can then communicate with the Evian server, which sits inside the ESNet core and has much more better access to the orchestrator to actually do much more intelligence at this level. In this way, we can keep the security constraints at the optimum, not allowing the client to freely communicate with the servers and make changes, but also give more intelligence and more software balancing out when it processes at the client and the server edges. So our overall architecture is described here, where we have our users which start off first. They generate an Evian client. The Evian client runs Rasa NLU and Rasa core. These extract entities and find what is the action required by the users. This is also then generating an RDF1, which is our relational data graph, and it can also then communicate that RDF to do policy and conflict checking in the Evian server. The Evian server is able to negotiate if there is a problem back to the client, who can also communicate back to the users. Eventually, once everything is rectified, they generate an RDF2. This maps actions to network devices, which are then rendered, and then that generates an RDF3, which is then sent to the network to actually run and configure the network for setting up the resources. A lot of this sets bring on a lot of capabilities, such as the server can do many optimization algorithms, clients can be more intelligent at the edge, and the renderer can have many tools linked to it. So having a very agile network at the back end. So many of our techniques are being mixed here. So we have the Rasa NLU open source code, which is activated at the Evian bot. We have a Slack API, which is used as the Evian client. This hosts the Evian bot. In the Evian server, we run our own optimization for resource management algorithms, which we constantly optimize at our own end. And eventually, we do use ontologies and RDF graphs to store the data across all of these different stages, which makes it easy to communicate the user requirements to the network as we go further. Designing the bot, we actually use the open source natural language processing system developed by Facebook called Rasa, which they use to actually ask questions like, what is the weather like tomorrow? Where are you based, for example? All of these are then communicated with intent and entities to the bot. The bot can then ask if any particular information is missing, ask for that, fill those up before it gets the required information back from the database. We actually extended Rasa NLU for network processing, where now we have our own network stories added to this, where the users can say, I want to transfer this particular file of data at this time. We set up our own stories with the start and the end and the value and the entities being recognized, and we can have many training stories which we can build over time. This is then extracted as JSON outputs. So it allows us to take an input and construct it into a JSON output of extraction, like what is the intent, what are the entities, what are the users asking for, and then that translates into action. So once the entities are intent is recognized, such as transfer, that intent transfer can then have an action associated with like which particular tool you want to call to do the transfer between the source and the endpoint. And over time, we can build these stories up to actually add more intelligence to the system. So RDF is stored at multiple levels of the intent. The first level provides a descriptive layer, which is a first sentence with requirements. Once that is communicated to the server, that's a second RDF, which is more prescriptive, where intent with user and network information is merged. And finally, at the third RDF, where the rendering layer sits, where we link the intent to the rendering tools themselves. An example of how the bot works is the bot can start by how can I help you? The user says, I want to transfer a file. The bot says, for more information from where to where, and then eventually what is the path of the input point, and then the user can actually give this. Again, because this is natural language processing, the user could actually give all of that information into one sentence and the bot wouldn't need to ask so many questions. So once the bot has all the information needed, it can process these training stories and actually build what the user is asking for, which is shown over here. That gets built into an example RDF as shown here, such as transfer has endpoints A and B, ANL and LBNL. What is the file information that needs to be transferred and what is the time they want the transfer to occur at. This is the first RDF. When the RDF is communicated to the server and everything is good, that is converted into this, which has more details on what the actual time is, what the actual protocols are being used, what are the source IP addresses, and any other login information for the users which could help identify if the user is correct. This second RDF and then is communicated back to the bot, which will check if the transfer can be done. If it's not instantiable, the bot can actually give them more information and actually do a negotiation stage. If not, then they could just say goodbye. The bot sits in a Slack API right now. We can actually render this very quickly and deploy it on everybody's computers. We have been testing and optimizing the natural language processing and the behind the scenes, so we've been able to bring down the query processing time to 4 seconds now, starting with 8. But eventually the main result we want to show is that rather than traditionally, if you are trying to set up an end-to-end link, it takes time because the users and the engineers need to communicate and they actually have to set up these transfers. With EVN, because a bot is setting everything up, we were able to actually reduce the time to install from hours to minutes. And this could actually be a great help to how we are setting up our networks in real time. In conclusion, we have multiple ways of going forward. We want EVN to connect to controllers using intent APIs. We have security permissions issues like Slack APIs need to manage security. Servers can access multiple orchestrators, and we also want to work with security teams in ironing out these details so it's easy transition from research to production. We want to add conflict and policy checking, and we also want to add more machine learning for prediction for the bot responses. It's very easy to change the Slack API into a GUI on top. We're still trying to find out what is the best way to do this to make life easy for network engineers. And the architecture allows us to have more tools to be added with automation, such as EVN can write out an Ansible code in the future, and that could be very, very beneficial to the network engineering community. If you have more questions, feel free to reach out to us. This work is funded under Project Daphne, where we are developing machine learning solutions for high-performance networks. This is my email address. Please feel free to reach out for any questions you have.